In this video, we're going to look at kernels and images of ring homomorphisms. So we're going to start with the definitions. We're going to let phi go from ring R to ring S be a ring homomorphism. We're going to define the kernel of phi to be the set kernel phi is equal to the set of everything inside ring R such that phi sends R to the zero element inside of S. And I kind of want to stress schematically what this is actually doing. So if this is R and this is S, we have somewhere over in S the zero element. And it turns out that everything inside of R that is inside the kernel is sent to the zero element. So if I'm an element inside the kernel, my arrow in the arrow diagram has to go to the zero element inside of S. So that's what the kernel is. Well, what I now want to do is I want to define the image of a ring homomorphism. So the image of phi taking R into S is defined as, it's usually written phi of the domain ring R is equal to the set of everything in the target ring S such that there exists an R inside capital R with phi of R equal to little s. Again, schematically what I want to do is I want to think about what this means. So here we have R and S. And this time what I'm going to do is I'm going to look at everything over here. And if I take them all over into S, there's going to be some subset. It might be all of S, but it might not be. There's going to be some subset of all of the answers. And this green part here would be phi of R. And the important idea is that if I take an element inside this chunk, right there, I know that there is somebody over here. So if this green thing here is my S, there is an R over here that is sent to that S. That's how I get inside the image of phi. But it's also equally important to realize that there may be elements such as this S hat that are not inside the image, and S hat not inside the image of phi means that S hat is not equal to phi of R for every single R inside the original, inside the ring R. Now what I want to do next is I want to look at a couple of examples of finding kernels and images of specific ring homomorphisms. So our first example is going to be based on a ring homomorphism that we studied in a previous video. So I want to recall that if we have phi going from the set of integers into the ring Zn given by phi of k is equal to R, where k is congruent to R mod n, and if we are given that, then we already know phi is a ring homomorphism. And so what I want to look at now is what is the kernel of phi and what is the image of phi. And I want to write the image of phi as phi of z. So what is the image and what is the kernel? Well, let's look at these two things separately. The kernel of our homomorphism is going to be any integer such that phi of that integer is equal to the 0 in Zn. And so k belongs to the kernel if and only if phi of k is equal to 0 inside Zn, but that's going to happen if and only if k is congruent to 0 mod n, and that's going to happen if and only if k is a multiple of n. So we now have the kernel. The kernel of this particular homomorphism is going to be the set of all multiples. In other words, it's going to be the set Qn, where Q is anything in Z. It's all of the multiples of n, but we can also write that set as n times Z, because this would be the set of n times something where the something is pulled from Z. And because multiplication inside the set of integers is commutative, these two sets are the same. Well, let's look at the image of phi. Oops, let's get my permanent pen. What is the image of phi? Well, here what I want to notice is that the residue classes, the remainders when we divide an integer by n, they are also a subset of the integers. And it's very easy to realize that phi of 0 is 0, phi of 1 is 1, phi of 2 is 2, all the way up to phi of n minus 1 is n minus 1. And this stuff says that the image of our ring homomorphism is actually all of Zn. And in this case, we are going to say that phi is onto Zn, or that phi takes or maps Z onto Zn. Those are all kind of mean exactly the same thing. Well, what I want to do next is I want to look at a second example that is a little bit different. So this time we're going to look at this. We're going to define a map phi from the real numbers to the 2 by 2 matrices with their entries drawn from the real numbers. And we're going to define this as phi of the real number r is going to be 0, 0, 0, r. And that clearly is a 2 by 2 matrix. And I'm going to shorten that notation up to just M22. Now, phi is a ring homomorphism because, first of all, R is a ring. It's a field, but that means it's a ring. And if I look at phi of R plus S, that's just going to be the matrix 0, 0, 0, R plus S. And a bit of matrix computation gives us this particular statement, and that's phi of R plus phi of S. So we have that phi preserves addition. We also have that phi preserves multiplication in very much the same way. Phi of RS would be the matrix 0, 0, 0, RS, and if you break that down, you can show that that matrix is the product of 0, 0, 0, R and 0, 0, 0, S. And that would be phi of R times phi of S. So this lets me know that phi is a ring homomorphism. But now I want to look at the kernel, and I want to look at the image of phi. So the kernel of phi. The kernel of phi is going to be anything inside the real numbers such that phi of that anything is the 0 matrix inside R22, which looks like the 2 by 2 matrix that has only zeros as its entries. Well, let's see. What do I know here? So I can say that R is going to be inside the kernel of phi if and only if phi of R is equal to that particular matrix, but phi of R is 0, 0, 0, R, so that matrix has to be this matrix. And the only way those two matrices can be the same is for that last element to be the same. In other words, these two matrices are the same if and only if R is equal to 0. So the kernel of our ring homomorphism is just the 0 inside the set of real numbers. And some vocabulary, this is said to be a trivial kernel. We will look at why it's called a trivial kernel in a later video. Well, to wrap this video up, we also need to look at the image of phi. So the image of phi, in other words, phi of all of the real numbers, is going to be the set of matrices inside M22 such that phi of a real number is equal to A. But our formula actually gives this one away. Phi of R is equal to 0, 0, 0 R. So the image of our ring homomorphism is going to be the set of everything that looks like 0, 0, 0 R, where that R is pulled from the real numbers. It's important to note in this case that phi is not onto, since the identity matrix is clearly not inside the image of R. There is no R inside capital R with phi of R equal to the 2 by 2 identity matrix. And hence we know that phi is not going to be onto the whole ring of matrices. And that ends this video.